Alright, in example it is another example of using substitution, alright, to reduce the DE into simpler form so that you can actually solve the DE in a much simpler way. Alright, so in this question your DE given is this, alright, so it's quite elaborate. Okay, so if you were to actually be given this DE and then you asked to solve it, alright, without using substitution, now it's going to be a major problem. Okay, because it's very complicated. So far you have learned variable separable. Then if you were to look at this equation on the right, it's quite impossible for you to separate the variables. Right. So not to worry, in such a question, alright, it will certainly be a substitution method. Alright, and the substitution that they actually want you to use is actually this one, y equals to u over x, and you are asked to show that after substituting, alright, the DE will actually be reduced to this. Okay, now if you were to see this DE here, right, now from this DE you know that you could actually do variable separable and then solve this DE quite easily. So this is actually the benefit of using substitution. Yeah, so now let's proceed with reducing the original DE to this simplified DE. Right, so we always start with y equals to u over x. Right, so from y equals to u over x, you could actually reduce it to, no, write it in this way, xy equals to u. Right. Now differentiating, alright, with respect to, let's say, x, alright, you will have x dy dx plus y equals to, again, u now is a variable, so if you differentiating u with respect to x, you will have du dx. Now the objective again is to get rid of the original DE here. This is the original DE. Alright, get rid of the y. Okay, and then change all the y to u. Okay, alright. So on the left side of the original DE, alright, left side is actually equals to x square y dy dx, and you know from here you actually have your x dy dx, but you want x square dy dx. Okay, so immediately I can actually write this as from here I will have x dy dx is equals to du dx minus y. Alright, so what I need to do is I need to multiply xy, in fact, so xy bracket du dx minus y. Okay, right, is that right? x y du dx, yeah, okay, so this is correct. Right, so that's left side. Alright, so on the left side from the original equation I will have xy du dx minus y. Alright, and then on the right side I will have x square y square minus xy squared plus 1. Right, so if I were to look at this closely, right, I will be able to observe that xy is actually u. Right, this xy here is actually u. Right, so you will have u du dx minus uy equals to x square y square minus in fact this the x square y square over here, the x square y square over here is actually u squared, right? Okay, minus again down here is actually x y y, so u y plus 1. Okay, so you know that this uy and then this uy can be cancelled off, right? So now what you have in the end is actually u du dx is equals to u squared plus 1, right? So we have shown, alright, that the original dE that I've highlighted in green can be reduced to this form. Okay, so up to this point everything is quite easy. Alright, so now our job is to actually solve this dE, right, given these initial conditions. Alright, so let's continue with it. Okay, so you know that from this simplified form of the dE after doing the substitution, it is actually quite easy to solve this because we can still apply our variable separable. Okay, variable separable method. Right, so when we shift all the u's to the left, alright, what you see is actually this. Okay, so we are at this stage now. So solving this is still not too bad, alright, because from here you can actually rewrite this in this form, 2u, alright, half, and then u squared plus 1 du, and this is dx. So on the left side, okay, you know that this is ln modulus of u squared plus 1, alright, and of course don't forget the half, equals to x plus an arbitrary constant c. Okay, right. Now the modulus of u squared plus 1, because u squared plus 1 is always bigger than 0 no matter what is the value of u, you can actually, alright, change, remove the modulus sign if you wish to. Right, so let's remove it now. Okay, so half ln, half ln u squared plus 1 equals to x plus c. Alright, and then this one can be reduced to ln u squared plus 1 equals to 2x plus, now when I cross multiply I will have 2c, right? But in order for us to be a bit more elegant in the way that we write down our arbitrary constant, 2c, we can always call it another by another letter if you wish to, but if you don't, alright, then we just retain the 2c. Okay, right. So now what you can do now is to convert the variable u back to y and x. Alright, bearing in mind that we were given this substitution y is equals to u over x. Alright, so from here, because y is equals to u over x, I can actually have ln xy square plus 1 equals to 2x plus 2c. Alright, so using the initial conditions here, right, I will be able to find out what is the value of c. Right, so okay, so using this, alright, I can get ln 1 plus ln 1 equals to 2 plus 2c. Right, so this implies that your c is equals to -1. Right, so at this stage we have found what is the value of the arbitrary constant. Okay, so with this value of the arbitrary constant, you can actually, right, put the arbitrary constant into this equation. Alright, so putting the arbitrary constant into this equation, you will actually reach this stage. Ln x square y square plus 1 equals to 2x minus 2. So now the general solution that you should arrive at is actually of this form, right? So this is a general the particular solution. Alright, because we already found out what is the value of the arbitrary constant, so it's no more a general solution, so it's a particular solution. Alright, so simplify this further. Alright, you should arrive to this equation because we are removing the ln, right? And then we can actually make it a little bit more elegant. Okay, alright, by making y square the subject, and of course make y the subject in this case. So this is the final answer for the particular solution. Alright, for x equals to 1, y equals to 0 condition.